We should get started.
Okay,
People may keep trickling in, but that's it.
perfect. Cool. So I think we are on chapter 5. So let me see if I can get the chat and things assigned. You guys can see my full screen, right? Hmm. Let's align the Zoom chat here. Okay, perfect. So before we start, actually, let me just share the Google Chrome. Yeah. So before we start, any questions from last 4 chapters that we read? Do we have good clarity? Like to recap very quickly, I think we started with the Morse code and we talked about how that encoding was decided, how that worked. And then we talked a bit about Braille, like how Braille was invented, what was its significance, and then we talked about the anatomy of a flashlight, where we discussed like how the cells work. We talked about the Ohm's law, and we talked about the how to measure power. I think that was named after James Watt. Any questions? No? Okay. So let's get started. So today we are going to talk with chapter 5. It's called Seeing Around Corners, which is a very interesting title if you think about it, because you actually cannot see around the corners. But let's see. You're 12 years old, and one horrible day, your best friend family moves to another town. You speak to your friend on telephone now and then, but telephone conversations just are not the same as those late night sessions with the flashlight blinking out Morse code. Your second best friend, who lives in the house next door to yours, eventually becomes your new best friend. It's time to teach your new best friend some Morse code and get late night flashlight blinking again. The problem is that your new best friend's bedroom window does not face your bedroom window. The houses are side by side, but the bedroom windows face the same direction. So, unless you figure out a way to rig up a few mirrors outside, the flashlights are now inadequate for after dark communication. Or are they? Maybe you have learned something about electricity by this time, so you decide to make your own flashlight out of batteries, light bulbs, switches, and wires. And you can see like how I'm sure like a lot of you might be confused that why did we talk so much about flashlight circuits and battery? And you will see how. I think this is again like one of the core foundations of our current digital infrastructure. So in first experiment, you wire up the batteries and switch in your bedroom. Two wires go out of your window across the fence into your friend's bedroom where they are connected to a light bulb. So basically the setup is something like this where you have a battery and a switch and your friend has the light bulb in their room. Although I'm showing only one battery, you might actually be using two. In this and future diagram, this will be the on and off switch. So everyone knows, I think this is the notation for on and off switch. It's fairly simple. When it is open, it's off. When it is closed, it's on. The flashlight in this chapter works the same way as the one illustrated in previous chapter, although the wires connecting the components for this chapter's flashlight are a bit longer, of course, because you are now reeling the wire from your room to your friend's room. So we can assume it's like close to 100 or 150 meters long wire now. And when you close the switch at your end, the light goes off at your friend's end. So as soon as I complete the circuit, the light gets up at my friend's house. So now you can send messages using Morse code. Once you have one flashlight working, this is still like a one-way communication. You can wire another long distance flashlight so your friend can send messages to you. So you can see like there is this dual kind of a setup where you have a battery and a switch, and like your friend can have a battery and a switch, and whenever they close circuit, like each other's house gets the light. Congratulations, so you have just rigged up a bi-directional telegraph system. You will notice that these two identical circuits are entirely independent of and unconnected to each other. In theory, you can be sending a message to your friend while your friend is sending a message to you. Although it might be hard for your brain to read and send the messages at same time. and you can again see like how, like where it is going. So you might also be clever enough to discover that you can reduce your wire requirements by 25% by wiring the configuration this way. So again, we first did something, a steel thread, and then we are now thinking on how to make it better. So instead of using two complete circuits for like two like bulbs to light up, we are basically unifying a single circuit where if you see that the negative terminals of two batteries are now connected, the circular the two circular circuits, battery to switch and bulb to battery, still operate independently. So basically anything that is going from bulb to battery to switch and bulb to battery to switch, they are still independently, but they share the wire across the negative terminal. Even though they are now joined as Siamese twins. I don't know who get this reference. Do you guys know what is a Siamese twin? No? It's a very old reference. I think they were very popular case of two kids who were born conjoined. So I think it's yeah, conjoined twins was like is the new term, but they used to be called Siamese twin because it was based on like this like couple of children who were born like joined together. A very interesting topic to read about like how it works. So sometimes it's two brains, one body, sometimes it's one brain, two body. But yeah. So this connection is called a common. In this circuit, the common extends from the point where the leftmost light bulb and battery are connected to the point where the rightmost light bulb and battery are connected. These connections are indicated by dots. So let's take a closer look at to assure ourselves that nothing funny is going on. So it will show us like what happens when a circuit becomes active. So first, when you depress the switch on your side, the bulb in your friend's house light up. The red wire shows the flow of electricity in the circuit. So I just completed the circuit. So this becomes the part of the circuit, and you can see that the other circuit is not active because it is not complete. So no electricity flows in the other part of the circuit because there is no place for electrons to go to complete a circuit. When you're not sending but your friend is sending, the switch in your friend's house control the light bulb in your house. Once again, the red wires show how electricity flows in the circuit. So now when my friend closes the circuit, you can see there is a complete loop that is going around here. But we were able to reduce our wiring requirements by sharing like a part of the circuit. And when you and your friend both try to send at the same time, sometimes both switches are open, sometimes one switch is closed, but the other one is open, and sometimes both switches are depressed. In that case, the flow of electricity in the circuit looks like this. So in this case, you can see this part of the circuit is not active, but when both are active, it is just forming like a giant big circuit where now these two batteries are in series. So now no current flows through the common part of your circuit. And if you think about your house wiring, if you have in your house those two-way switches, right, where there is a light, where there is one switch which is maybe next to your bedroom, and you would have seen this in hotels as well, and there is a next switch which is like in front or like a panel far away, that also uses the same common circuit. So by using a common to join two separate circuits in one circuit, we have reduced the electrical connection between two houses from 4 wires to 3 wires and reduced our wire expense by 25%. If we had to string the wires for a very long distance, we might be tempted to reduce our expenses even more by eliminating another wire. Unfortunately, this is not feasible with the 1.5 volt D cells and small light bulb. But if we were dealing with 100-volt batteries and much larger light bulbs, it could certainly be done. Here is the trick. Once you have established a common part of the circuit, you don't have to use wire for it. You can replace the wire with something else. And what you can replace it with is a giant sphere, approximately 7,900 miles in diameter, made up of metal, rock, water, and organic material, most of which is dead. The giant sphere is known to us as Earth. And now again, like some of you who would have done some wiring in your house would know like a massive role the earthing, the top terminal in your switch plays when you're using electronics. So when I described the good conductors in the last chapter, I mentioned silver, copper, and gold, but not gravel and mulch. In truth, the earth is not such a hot conductor, although some kinds of earth, damp soil for example, are better than others, such as dry sand. But one thing we learned about conductors is this: the larger the better. A very thick wire conducts much better than a very thin wire. And that's where the earth excels. It's really, really, really big. To use the earth as a conductor, you cannot merely stick a little wire into the ground next to the tomato plants. You have to use something that maintains a substantial contact with earth, and by that I mean a conductor with a large surface area. One good solution is a copper pole of at least 8 feet long and half inch in a diameter. That provides 150 square inches of contact with the earth. You can bury the pole into the ground with a sledgehammer and then connect a wire to it. Or if the cold water pipes in your home are made of copper and originate in the ground outside the house, you can connect a wire to the pipe. So I think this is a very common practice also. So like whenever you study like how skyscrapers are made, like even I think Burj Khalifa has a really nice documentary. One of the biggest challenges they had was like what happens if a lightning strikes around them. So if you think of a building, it is made out of so those buildings are made out of like huge metal steel and metal blocks, and it uses a lot of metal and glass for the construction. So any kind of lightning can be very detrimental to the building and the people inside it. So they spent a lot of time building. That's why you see a lot of big buildings, they have like this huge pole sticking up on the top. That is to provide earthing. So the case is like if a lightning strike, it goes to the pole and then it bypasses the whole building and it directly goes into the ground so that they can disperse the electricity safely. So, an electrical contact with the earth is called earth in Great Britain and ground in America. So, I think there is a different terminology, but we practice British English, so we talk about that as earth. A bit of confusion surrounds the word ground because it is also often used to refer to a part of circuit where we have been calling the common, which we have been calling the common. In this chapter, and until I indicate otherwise, a ground is a physical connection with the earth. When people draw electrical circuits, they use this symbol to represent the ground. Like a lot of you might already know, right? Like we have used this in like physics in our elementary and senior schooling. So electricians use this symbol because they don't like the time to they don't like to take the time to draw an 8-foot copper pole buried in the ground. Let's see how this works. So we begin this chapter by looking at a one-way configuration like this: a battery, a switch, a circuit, and a bulb, your house and your friend's house. If you were using a high voltage battery and light bulbs, you would need only one wire between your house and your friend's house because you could use earth as one of those connectors. So look at this. So instead of now completing the circuit, you can basically connect your battery to the earth side of your house, create a wire, and you can create like something like this where there is bulb and there the friend's house, the other terminal is also grounded or earth, connected to earth. When you turn on the switch, the electricity flows like this. So electricity goes from here and then it just goes back. And you might think like, but is it the same circuit that is being completed? And how do electrons know that now they have to go back? They don't. We talked about this in a couple of chapters back, where all electrons are homogeneous. They are exactly the same. So it doesn't matter where they are coming from. So the electrons come out of Earth at your friend's house, go through the light bulb and wire, the switch at your house, and then go into the positive terminal of the battery. The electrons from the negative terminal of the battery goes into Earth. You might also want to visualize electrons leaping from a 8-foot copper pole buried in the backyard of your house into Earth and then scurrying through Earth to get to the 8-foot copper pole buried in the backyard of your friend's house. But if you consider that the Earth is performing this same function for many thousands of electrical circuits around the world, you might ask, how do electrons know where to go? Well, obviously they don't. A different image of Earth seems much more appropriate. Yes, the Earth is a massive conductor of electricity, but it can also be viewed as both a source and a repository for electrons. You can think of Earth as a giant breadboard, if you know what that used to be. Even breadboard had some limitations, but like a very well crafted PCB in a way. The PCB is a printed circuit board. You know, some of you, if you don't know. So the Earth is to electrons as an ocean is to drops of water. The Earth is a virtually limitless source of electrons and also a giant sink for electrons. The earth, however, does have some resistance. And that's why we cannot use the earth ground to reduce our wiring needs if we are playing around with 1.5 volt D cells and flashlight bulb. The earth simply has too much resistance for low voltage batteries. And if you have ever used, I'm forgetting the name, I think there is an instrument in physics lab, but where like maybe even a transformer in a circuit. So you can see like as you increase voltage, each bulb based on what filament and what voltage they are rated for will not start to light up until you have crossed a certain amount of volt, and then it crosses the potential barrier and then the bulb lights up. So it's a similar case with earth, that if you use just 1.5 volt cells and flashlight bulb, that is not enough for your circuit to work, because there is just a lot of resistance in the materials that are using, and 1.5 volts of potential is not good enough. You will notice that the previous two diagrams include a battery with a negative terminal connected to the ground. I'm not going to draw this battery connected to the ground anymore. Instead, we are just going to simplify the circuit. So I'm going to use the capital letter V, which stands for voltage. The one-way light bulb telegraph now looks like this. So basically, we have a voltage here and a switch, and then my friend's house has a bulb, which is again connected to the earth. The V stands for voltage, but it can also stand for vacuum. Think of V as electron vacuum and think of ground as an ocean of electron. One again very interesting thing that I always used to think in a wrong way: the electrons are not flowing from battery to bulb to the ground. It's the other way around. Your electrons flow in the opposite direction of your electricity. So when you connect the circuit, electrons flow from the ground to the bulb to the switch to your voltage source. So you can think of this as a repository and this as a sink. And then you are just trying to do some transfer of electrons. And on the way, there is a bulb which has a tungsten filament, which has a certain resistance, and it lights up when current goes through it. The electron vacuum pulls the electron from the earth through the circuit, doing the work along the way, such as lighting the bulb. The ground is also sometimes known as the point of zero potential. This means that no voltage is present. A voltage, as I explained earlier, is the potential of doing work, much as a brick suspended in air is a potential source of energy, kinetic energy. The zero potential is like a brick sitting on the ground, and there is no place left for it to fall, so it is fairly stable. In chapter 4, one of the first things we noticed was that circuits were circles. Our new circuit does not look like a circle at all. It is still one, however. You could replace the V with a battery and with the negative terminal connected to the ground, and then you can draw a wire connecting to all the places you see the ground symbol, and you would end up with the same diagram that we started in this chapter. So if like I take all the grounds and I connect them, it starts resembling like a very simple and very similar circuit. So with the help of couple of copper poles or cold water pipes, we can construct a two-way Morse code system with just two wires crossing the fence between your house and your friends. So now I think we don't even need to have that common part where I think this was connected to the negative part of the battery. This circuit is functionally the same as the configuration shown previously, in which three wires cross the fence between the house. In this chapter, we have taken an important step in the evolution of communications. Previously, we had been able to communicate with Morse code, but only in a straight line of sight and only as far as the beam from flashlight would travel. But by using wires, we not only we have we constructed a system to communicate around corners beyond the line of sight, but we have freed ourselves of limitation of distance. We can communicate over hundreds and thousands of miles just by stringing longer and longer wires. Well, not exactly. Although copper is a very good conductor of electricity, it's not perfect. The longer the wires, the more resistance they have. The more resistance, the less current that flows. And the less current, the dimmer the light bulbs. So, how exactly can we make the wires? That depends. And that's why I think in your house, if you ever talk to an electrician, based on what kilowatt hour meter you get, your wiring needs to be of a specific gauge. Because if the current is very high and wires are thin, the wires melt and burn, right? And if the current is too low and wires are too thick, then in that case, like your current will not have enough potential to do the work that it needs to do. This is why I think if a lot of you grew up especially in tier two or tier three cities, having a transformer with big things used to be a common sight. I remember growing up with a transformer on top of a fridge, on side of a TV, like anything that would need a lot of current, there will be a, sorry, not transformer, a stabilizer, a voltage stabilizer that will be there that will stabilize the voltage in case the voltage source is very erratic. And it uses a bunch of capacitors and some imp to reduce the impedance. But yeah, but it's a interesting thing to look at. But I think eventually, like I think we have gotten really better at providing good quality voltage. So it's not no longer the case. Although I think for some things like AC, people still have voltage stabilizers. But if you don't use it and you just plug your AC in the wall, it will still work for the most part. So, so how long can we make the wires? That depends. Let's suppose that you are using the original 4-wire bidirectional hookup without the grounds and commons, and now you're using the flashlight batteries and light bulbs. To keep your costs down, you may have initially purchased some 20 gauge speaker wire from Radio Shack at $9.99 per 100 feet. Speaker wire is normally used to connect to your speaker to your stereo system. So you all have seen that like wire. It's like basically an auxiliary cable. It has two conductors, so it is also a good choice for our telegraph system. If your bedroom and your friend's bedroom are less than 50 feet apart, this one roll of wire is all you need. The thickness of wire is measured in American wire gauge or AWG. The smaller the AWG number, the thicker the wire, and also the less resistance it has. The 20 gauge speaker wire that you bought has a diameter of about 0.032 inches and has a resistance of about 10 ohms per 100 feet. So this is how you donate. Uh, the notion is for like what is the resistance per what distance, or you can simplify it and say that it is 1 ohm for 100-foot round trip distance between the bedrooms. So that's not bad at all. But what if we strung the wires out for a mile? A mile is a 1.6 kilometers. The total resistance of the wire would be more than 100 ohms. Recall from the last chapter that our light bulb was only 4 ohms. So from Ohm's law, we can easily calculate that the current through the circuit will no longer be 0.75 amp, which is 3 divided by 4, as before, but now it will be less than 0.03 amps. So 3 volts divided by more than 100 ohms, because that is the resistance of wire that gets added to the circuit. Almost certainly that would not be enough current to light the bulb. Using thicker wire is a good solution, but that can be expensive. 10 gauge wire, which Radio Shack sells as automotive hookup wire, which basically you use to jumpstart your battery of your car, and that is a little bit of a thicker wire than your auxiliary cable, is they sell it for $11.99 for 35 feet, and you would need twice as much because it only has one conductor rather than two, and is about 0.1 inch thick, but has a resistance of only 1 ohm per 1000 feet or 5 ohm per mile. Another solution is to increase the voltage and use the light bulbs with much higher resistance. For example, a 100-watt light bulb that lights a room in your house is designed to be used with 120 volts and has a resistance of about 144 ohms. The resistance of wires will then affect the overall circuitry much less. So I think that's the way. If you have a very low power bulb, you will need to basically ensure your wiring is correct. If you have a very larger one, it will work with the higher potential. You can increase the voltage and then it will work nicely. So these are the problems phase 150 at give or take 25 more years, so around 175 years ago, since this book was published in 1999, by the people who strung up the first telegraph system across America and Europe. Regardless of the thickness of the wires and the high levels of the voltage, the telegraph wires simply could not be continued indefinitely. At most, the limit for a working system according to this scheme was a couple hundred miles. And that's nowhere close to spanning thousands of miles between New York and California, which are like on different coasts of North America continent. The solution to this problem, not for flashlights, but for clicking and clacking the telegraphs of yesteryears, turns out to be a simple and humble device, but one from which an entire computer can be built. So this was our chapter seeing around the corners. Before we move to the next chapter, any questions? And we are basically talking about the foundation of how telegraph was laid across like different countries. If you have questions, please raise your hand. And you can also raise your hand otherwise if you have a question in between, and I'm happy to help. No questions? Okay. Should we move on to the next one? Can I see a thumbs up? Cool. And I think this is one thing that people also don't realize. The internet that we use, it seems like it is wireless, but 95% of internet is basically just giant copper wires going through the bed of ocean and connecting different nodes to each other. So if you want to see the internet wire diagram, wiring diagram, oh, not this one. Yeah, so internet looks mostly like this. It's nothing but a giant network of the wires interconnected to each other so that the network can go through. And then for smaller distance, you can use like your radio towers and some of the other things. And communication is the bedrock of communication infra is the bedrock of internet. I don't know, anyone of you here has used dial-up in the past? The dial-up internet before broadbands and used to be a thing. Sunny, I can see Sunny is nodding. Oh, it used to be amazing. We had a MTNL broadband connection. I think the initial speed that we used to get was around 16 kbps. Uh,
64 kbps is where I started, and
oh,
you used to hear weird noises when you picked up the
yeah.
phone. If you do that, etc. It was interesting. I did not realize Raghu sir is here as well.
Oh,
Uh, yeah,
nice.
but yeah,
So, yeah, that was fun. I think it used to make some noises and you had to keep your phone off. Like you cannot take a call because your internet, your bits and bytes used to travel through your phone lines. It was a really interesting time and very expensive. So I think VSNL and MTNL, basically VSNL was the only internet provider initially. There were no private players, and that happened much later. Okay, so let's talk about chapter 6, telegraphs and relay. Samuel Finley Breeze Morse was born in 1791 in Charleston, Massachusetts, the town where the Battle of Bunker Hill was fought and which is now the northeast part of Boston. In the year of Morse's birth, the United States Constitution had been ratified just 2 years before, and the George Washington was serving his first term as president. So, ratified is nothing but a word for that. A lot group of people got together, and there was a consensus that this should be our constitution. So, we do a lot of ratification even in tech. Like whenever there is a new RFC, we use the word ratified. That let's ratify this with the team. Catherine the Great ruled Russia. Louis XVI and Marie Antoinette would lose their heads 2 years later in the French Revolution. And in 1791, Mozart completed The Magic Flute, his last opera, and died later that year at age of 35. Oh yeah, he was pretty young when he died. Morse was educated at Yale and studied art in London. He became a successful portrait artist. His painting General Lafayette hangs in the New York City Hall. In 1836, he ran for the mayor of New York City on an independent ticket and received 5.7% of the vote. He was also an early photography buff. Morse learned how to make the, I don't know how to spell this, let's see, daguerreotype photograph from Louis Daguerre himself and made some of the first. Let's search what this is. So, daguerreotypes. This is something I don't remember. Okay, daguerreotype. Oh, it's the style of photos. I think one of the first practical photographic process invented by this guy in 1930s. Oh, this is why a lot of old photos look like this. They have this very similar trait. And I saw some model, I think Gemini or not Gemini. I think I saw some research where they were trying to convert these photos back into modern photos. And I think these photos had a very different way of capturing the contrast and the details in your face. So that's why they all used to look like these people are very pale and like very ghostly kind of features. Interesting. So let's see. Yeah. In 1940, he taught this process to the 17-year-old Matthew Brady, who, with his colleagues, would be responsible for creating the most memorable photographs of Civil War, Abraham Lincoln and Samuel Morse himself. But these are just the footnotes to an eclectic career. Samuel F.B. Morse is best known these days for his invention of the telegraph and the code that bears his name, Morse code. The instantaneous worldwide communication we have become accustomed to is relatively recent development. In early 1800s, you could communicate instantly and you could communicate over long distances, but you could not do both at same time. Instantaneous communication was limited to as far as your voice could carry without any amplification, or as far as the eye could see, aided perhaps by a telescope. Telescope was already invented in 1600s. Communication over long distances by letter took time and involved horses, trains, or ships. For decades prior to the Morse invention, many attempts were made to speed long distance communication. Technically simple methods employed by a relay system of men standing on hills waving flags in a semaphore codes. Technically more complex solutions used large structures with movable arms that did basically the same thing as men waving flags. The idea of the telegraph, literally meaning far writing, was certainly in the air in early 1800s, and the other inventors had taken a stab at it before Samuel Morse began experimenting in 1832. In principle, the idea behind an electrical telegraph was simple. You do something at one end of the wire that causes something to happen on the other end of the wire. This is exactly what we did in the last chapter when we made the long distance flashlight. However, Morse could not use a light bulb as his signaling device because a practical one would not be invented until 1879. Morse relied upon the phenomenon of electromagnetism. So electric bulb was not even a thing yet, but he just wanted to have like a cause and causation like effect. Like whenever I could close a switch, something should happen on the other end. So if you take an iron bar, wrap it with a couple hundred turns of thin wire, and then run a current through the wire, the bar becomes magnet. Everyone, we have studied that, right? Electromagnets. It's a very fun example also. If some of you haven't done that, if you take like a large screw or a nail and you wind a wire across it and then try to connect like a 3-volt battery with it, you will see that it becomes a magnet when the circuit is complete. A really fun experiment to do. So there is enough thin wire in the electromagnet. Sorry, it then attracts other pieces of iron and steel. There is enough thin wire in the electromagnet to create a resistance great enough to prevent the electromagnets from constituting a short circuit. Remove the current and the iron bar loses its magnetism. So you can magnetize any iron. And this is very, very it is used in multiple applications like around manufacturing today. Electromagnets are used almost everywhere. Even I think in your phone there will be a bunch of electromagnets trying to do some of the things. So the electromagnet is also the foundation of the telegraph. Turning the switch on and off at one end causes the electromagnet to do something on the other end. Morse's first telegraphs were actually more complex than the ones later evolved. Morse felt that a telegraph system should actually write something on a paper, or as computer users would later phrase it, produce a hard copy. Right? Because you can see one limitation with the telegraph system that someone has to be on the receiving end to get the message so that they can look at the bulb or some action that is happening and translates into dot and dashes, and then those dots and dashes back into our like language. So this wouldn't necessarily be words, of course, because that would be too complex for that time. You could not really carry, the signals could not really carry voice. But something should be written on paper, whether it be squiggle or dots and dashes. Notice that the Morse was stuck in the paradigm that requires paper and reading, much like the Valentine Hawes notion that books for the blind should use raised letters of alphabet. Although Samuel Morse notified the patent office in 1836 that he had invented a successful telegraph, It wasn't until 1843, 7 years later, that he was able to persuade Congress to fund a public demonstration of device. The historic day was May 24th, 1844, when a telegraph line rigged between Washington, D.C. and Baltimore, Maryland, successfully carried the biblical message, "What hath God wrought?" The traditional telegraph key used for sending message looked something like this. And it's very funny, it still looks like this. Hasn't evolved yet. And on a tangent, this reminds me of this really nice book. If some of you are interested in the design of everyday things. This is one of my favorite books that I read like a few years back. And it talks about a lot of things that we use day to day, where the design has not changed ever since those things were invented. So for example, your glasses, the specs that you wear, they have been like same for last few hundred years. Design of a spoon, like few probably thousands of years, it has been exactly the same. So I think this is also very similar to the same thing. Anyway, so despite the fancy appearance, this was just a switch designed for maximum speed. The most comfortable way to use the key for long periods of time was to hold the handle between thumb, forefingers, and middle fingers and tap it up and down. Holding the key down for a short period of time produced a Morse code dot. Holding it down longer produced a Morse code dash. The other end of the wire was a receiver that was basically an electromagnet pulling a metal lever. Originally, the electromagnet controlled a pen, while the mechanism using a wound up spring slowly pulled a roll of paper through the gadget. It's all mechanical and it's all manual. Roll of paper. The attached pen bounced up and down and drew dots and dashes on the paper. It's basically like a very early form of printer. So I think I have a comment, Sachin. Found a link to the book. Someone exposed this. Oh, Sunny, you also have it on your bookshelf. Like a really nice book. Yeah. Yeah, I think you can find a lot of things on internet if you know how to use Google really well. Google has a lot of hidden ways that you can find, and you can search FTP servers and file types. Yes. So yeah, so there was a pen, and then there will be a wound up spring that will take a paper, and then it will pull it through the gadget, and the pen will go up and down to draw dots and dashes. A person who could read Morse code would then transcribe the dots and dashes into the words. Of course, we humans are a lazy species, and the telegraph operator soon discovered that they could transcribe the code by simply listening to the pen bounce up and down. The pen mechanism was eventually eliminated in favor of a traditional telegraph sounder, which looked something like this. When the telegraph key was pressed, the electromagnet in the sounder pulled the movable bar down and made a click sound. So it's basically, you can see this is suspended. There is a lever, and it will just go down and hit this piece here. So when the key was released, the bar sprang back to its normal position, making a clack noise. The fast click clack was a dot. The slower click clack was a dash. And you can probably go to YouTube and also hear like how it works. Maybe we'll try and see. Like, I'm not sharing with sound. Okay, let me actually reshare my tab. Oh, it will need me to restart Zoom. Okay, so you guys can do it. So the key, the sounder, a battery, and some wires can be connected just like the light bulb telegraph in the preceding chapter. So this is your telegraph station. There is a small battery or a voltage source. And then there is my friend's telegraph station, which has an electromagnet with this suspended metal arm. As we discovered, you don't need two wires connecting the two telegraph stations. One wire will suffice if the earth provides the other half of the circuit. As we did in the previous chapter, we can replace the battery connected to the ground with capital V. So the complete one-way setup looks something like this, where there is a voltage source, and then there's connected to electromagnet, and then that's connected to a earth. Two-way communication simply requires another key and sender. This is similar to what we did in preceding chapter. The invention of telegraph truly marks the beginning of communication. For the first time, people were able to communicate further than the eye could see or the ear could hear, and faster than a horse could gallop. Basically, the snail mail. Uh, that this invention used a binary code is all the more intriguing. In the later forms of electrical and wireless communications, including the telephone, radio, television, binary codes were abandoned, only to later make an appearance back in computers, compact disc, digital video discs, digital satellite television broadcasting, and high definition TV. Morse telegraph triumphed over other designs in part because it was tolerant of bad line conditions. If you strung a wire between a key and sounder, it usually worked. Other telegraph systems were not quite as forgiving. But as I mentioned in the last chapter, the big problem with the telegraph lay in the resistance of the long lengths of wire. Although some telegraph lines used up to 300 volts and could work over a 300-mile length, wires could not be extended indefinitely. One obvious solution is to have a relay system. Every couple of hundred of miles or so, a person equipped with a sounder and a key could receive a message and send it forward, hence the name relay. So you have seen some racings where they pass a baton, they run and then they pass it and they call it like a relay race. So, and also I think this is a pattern that you will see in a lot of places. Like if you start thinking about this, like a message you're sending is going through a relay. Me talking to this line, this is going to do multiple relays to get to each of your receivers end in your place. Even I think for sound, we use a lot of amplifiers. That's also like a part type of a relay. So now imagine that you have been hired by the telegraph company to be a part of this new relay system. They have put you in the middle of nowhere between New York and California in a little hut with a table and a chair. Oh yeah, Aziz says Lyft also uses relay. Yep, a relay circuit is used like almost everywhere around the house. It's also a lot more fault tolerant. And then if something breaks, you don't have to change the whole wiring, you just change the part that is broken. So yeah, so I think they have put you in middle of nowhere between New York and California with a little hut, a table and a chair. A wire coming through the east window is connected to a sounder. Your telegraph key is connected to a battery, and the wire going out is through the west window. Your job is to receive the messages originating in the New York and to send them eventually to reach California. It's something like a router, like how a router works to route the traffic in your house. At first, you prefer to receive an entire message before resending it. You write down the letters that corresponds to the click of the sound, and when the message is finished, you start sending it using your key. Eventually, you get a knack of sending the message as you are hearing it without having to write the whole thing down. It saves time. So as you are hearing it, this is the concept of buffering. So you buffer some messages and then you start sending it forward. One day, while resending a message, you look at the bar on the sounder bouncing up and down, and you look at your fingers bouncing the keys up and down. And you look at the sounder again, and you look at the key again, and you realize that the sounder is bouncing up and down the same way the key is bouncing up and down. So you go outside, pick up a little piece of wood, and you use that wood and some string to physically connect the sounder and the key. So something like this. And now it works by itself. And see, it's nothing new, right? I think from last few hundred years we have been trying to eliminate the human effort, and nothing has changed. Now we have self-driving cars, right? Like because human is always the slowest and the weakest element who needs to sleep, who needs to rest, who needs insurance, who needs food, and who needs motivation to do the work. But when you automate something, it just works end to end. So now it works by itself, and you can take rest of the afternoon off and go fishing. It's an interesting fantasy, but in reality, Samuel Morse had understood the concept of this device early on. The device we have invented is called a repeater or a relay. And a lot of these words are used again when in our network terminology, but they all originate from these parts. So a relay is like a sounder in that incoming current is used to power an electromagnet that pulls down the metal lever. The lever, however, is used as a part of a switch connecting a battery to an outgoing wire. In this way, a weak incoming current is amplified to make for a strong outgoing current. Drawn rather schematically, the relay looks something like this. So there is an input coming to this magnet. This is connected to earth. There is a voltage source, and then there is an out here. This is like a switch. So when an incoming current triggers the electromagnet pulls down the flexible strip of metal that acts as a switch to turn on the ongoing current. So instead of you using this to bang on that, which can have a lot of problems where the stick can break, it can get misaligned, and it's more moving parts. The more moving parts you have, the higher chance of failure and maintenance there is. We actually just made this sounder part into a switch. So as soon as this electromagnet pulls it back, we complete a circuit, we have one more battery, and then we send a new signal fresh to the forward one. So this is how it amplifies or it plays the signal again. So the telegraph, a key, so a telegraph key, a relay, and sounder are connected more or less like this. So your telegraph station, this is somewhere far away, and in middle there is a relay station, which is an electromagnet that is completing the circuit, and then it's a replaying the same signal, and then your friend at a telegraph station has another sounder to them. So the relay is a remarkable device. It's a switch, surely, but a switch that's turned on and off not by human hands but by a current. You could do amazing things with such devices, and you could actually assemble much of a computer with them. Oh, I see some text. Okay. Yes, this relay thing is much too sweet an invention to leave sitting around the telegraphy museum. Let's grab one and stash it inside our jacket and walk quickly past the guards. This relay will come in very handy, but before we can use it, we are going to have to learn to count. So that was chapter 6. Any questions, comments?
On the last part where the electromagnet just pulls the key, what I was
Mhm.
thinking is that might be very physicky, but what I was thinking, whenever there is a electromagnetic field, uh, due to flux, an electric current is also formed. So
Hmm.
maybe in future this might have been not only key. As soon as the electromagnetic current or electric magnetic field comes, the circuit automatically joins due to the flux around it.
Yep. It is going to get much more simple after that because we will learn like how to carry the signal. So I think the whole digital infrastructure is like zeros and ones, right? In current. So you don't even need like electromagnet is still like a physical moving piece, which requires like a certain voltage threshold to work and become magnetic. But this worked because we had just started generating electricity and we did not really care too much about like how much electricity we are using. But if you think about it, if you could have a way of capturing the on and off state of just the current, not even the electromagnetic current, just the electrons flowing in the wire, you basically again have the same system, but with much less voltage requirement. Okay, so this is a small chapter. I think we have 8 minutes, 7 minutes. We can go for it. Do you guys want to go and do you guys want to stop? We can complete this chapter in 5 to 10 minutes, I guess. Okay, go forward. Okay, so chapter 7 is our 10 digits. And let's start. So, the idea that language is merely a code seems readily acceptable. Many of us at least attempted to learn a foreign language in high school. It's funny, we all are speaking a foreign language actually. Uh, so, we are willing to acknowledge that the animal we call a cat in English can also be gato, chat, katze, koika, or kata. Numbers, however, seems less culturally malleable. Regardless of the language we speak and the way we pronounce the numbers, just about everybody on the planet we are likely to come in contact with on this planet writes the things the same way. So it's 1 to 10. Isn't mathematics called a universal language for a reason? So when I was in engineering, my professor used to call mathematics the language of gods because mathematics is like the always the most purest form of language you can write, where if you write a function or a like some equation in mathematics, it will always mean exactly what it is. Like there is no way someone who understands maths can ever misinterpret that. Language, on other hand, can be misinterpreted based on context, the person who is speaking and how it is spoken. So numbers were certainly the most abstract codes we deal on with a regular basis. When we see the number 3, we don't immediately need to relate it to anything. We might visualize 3 apples or 3 of something else, but we would just be as comfortable learning from the context that the number refers to the child's birthday, or it can be a television channel, a hockey score, or the number of cups of flour in a cake recipe. Because of our numbers are so abstract to begin with, it's more difficult for us to understand that this number of apples does not necessarily have to be denoted by symbol 3. Much of this chapter and the next will be devoted to persuading ourselves that this many apples can also be indicated by writing 11. And this is something I also used to think when I grew up, like, why do we write the way we do? And I think eventually it's just like a mutually agreed construct that keeps us going without falling into the trap of discussing like trivial things and getting caught in the loop of doing that. So let us first dispense with the idea that there is something inherently special about the number 10. The most civilizations have based their number systems around 10. Can anyone tell why? It's simple, right? Look at your hands. So, from the very beginning, the people used their fingers to count. Had our species developed processing 8 or 12 fingers, our way of counting would be a little different. It is no coincidence that the word digit can also refer to the fingers and toes as well, as the numbers or the words five and fist have similar roots. So, five fist. So, in that sense, using a base 10 or a decimal from the Latin of 10, number system is completely arbitrary. Yet we endow numbers based on 10 with almost a magical significance and give them special names. 10 years is a decade, 10 decades is a century, 10 centuries is a millennium, thousand is a million, 1,000 million is a billion. These numbers are all power of 10. And we also say 10 raised to the power 9 or something. Most historians believe that the numbers were originally invented to count things such as people, possession, transactions in commerce. For example, if someone owned 4 ducks, this might be recorded with drawings of 4 ducks initially. Eventually, the person whose job is to draw the ducks thought that, why do I have to draw 4 ducks? Why can't I draw 1 duck and indicate that there are 4 of them with, I don't know, a scratch mark or something? Yeah, our logs are also on base 10 that we use, Sachin. That's correct. So, and then there comes the day when someone had 27 ducks and the scratch mark got ridiculous because now like it's very hard to count that and I will spend probably more time than counting the number of ducks that are there. Someone said there's got to be a better way and the number system was born. One of the early number systems, only Roman numerals are still in common use. And this is a very interesting one. So I think this was also solved where this is not talking about it. So I think if I go here, like you may have seen this, so like they would, oh, sorry, it's editing something. So 1, 2, 3, 4, and then for 5, they used to do this, like you would have seen it. And then the idea would be that you would have these bunch of lines, and then you will count in the multiple of fives. And then that solves the problem somewhat of how do I know what this is. But it still gets ridiculous. Like if you have to now count 100 ducks, instead of just writing like 100, like we can write here, you would have to draw 20 of these things. Okay, so, and yeah, it's very interesting. Of all the early number systems, only Roman numerals are still in common use. Yeah, it's called a tally. Oops, sorry. So you find them on the faces of clock and watches used for dates, on monuments and statues, for some page numberings in the book, and for some items in an outline, and most annoyingly for the copyright notices in the movies. The question, what year was this picture made, can often be answered only if one quick glance is enough to decipher MCMLII at the tail end of the credits goes by. The 27 ducks in Roman numerals is like XX7. So this is X is 10, 10, and then 7. The concept here is easy enough. X stands for 10 scratch marks and V stands for 5 scratch marks. And you can see like how it originated from scratch marks initially. So 1 is 1 scratch mark. Roman numeral is very in between like our current numbers and this scratch methodology. And you can try to think like how they started denoting things as they had more and more things to count. The symbol of Roman's numeral symbols that have survived today are I, V, X, L, C, D, M. The I is 1. This could be derived from a scratch mark or a single raised finger. The V is probably a symbol for a hand and stands for 5. Two V's make an X, which stands for 10. So it's, you see like V and V. So there's basically formed like an X. The L is a 50. The letter C comes from the word centum, which is the Latin word for 100, and D is 500, and finally M comes from a Latin word mile or 1,000. Although we might not agree, for a long time, Roman numerals were considered easy to add and subtract, and that's why they survived so long in Europe for bookkeeping. Indeed, when adding two Roman numerals, you simply combine all the symbols from both numbers and then simplify the result by just using a few rules. So 5i's becomes makes a V, 2V makes an X, and 5x makes an L, and so forth. But multiplying and dividing Roman numerals is difficult. Many other early number systems, such as that of ancient Greeks, are similarly inadequate for working with the numbers in a sophisticated manner. While the Greeks developed an extraordinary geometry, it's still taught virtually unchanged in high school today. The ancient Greeks are not known for their algebra. The number systems we use today is also known as Hindu Arabic or Indo Arabic. It's of Indian origin but was brought to the Europe by Arab mathematicians. Of particular renown is the Persian mathematician Muhammad ibn Musa al-Khwarizmi, whose name we have derived the word algorithm. Oh, I remember reading this. Like there was this book in engineering called ADA, Algorithmic and Design Analysis, and I think that also mentioned this. So the word algorithm is defined from probably a mispronunciation of his name by Europeans, who wrote a book on algebra around AD 825, and that used the Hindu system of counting. Our Latin translation dates from AD 1120 and was influential in hastening the transition throughout Europe from Roman numerals to our present Hindu Arabic systems. And if you think of this, this happened almost 1,000 years ago. And the Roman numerals have still survived, right? Like we write our education standards with Roman numerals, and it's pretty crazy to think about like how old this construct of language is. So the Hindu Arabic number system was different from the previous number systems in three ways. The Hindu Arabic number system is said to be positional, which means that the particular digit represents a different quantity depending on where it is found in the number. When the digit appears in a number, where the digits appear in a number is just as significant, actually more significant than what the digits actually are. Both 100 and 1 million have only one single one in them. Yet we all know that a million is much larger than 100. Virtually all early number systems have something that the Hindu Arabic system does not have, and that is a special symbol for number 10. In our number system, there is no special symbol for 10. We write it with a combination of 1 and 0. On the other hand, virtually all early number systems are missing that error of which number, and which turns out to be much more important than the symbol for 10, and that is the 0. Yes, the 0, the lowly 0 is without doubt one of the most important inventions in history of numbers and mathematics. It supports positional notations because it allows for the differentiation of 25 from 205 and 250. The zero also eases many mathematical operations that are awkward in non-positional systems, particularly multiplication and division. The whole structure of Hindu Arabic numbers is revealed in the way we pronounce them. Take 4825 for instance, we say 4825. So we basically break it down, and this is something now we do very subconsciously. But if you go back to your elementary school, like your kindergartens and your first and second standard, this is how they used to teach us. Like you would, in India, we would look from the right side, we will first put three commas and then two commas each, the Indian system, and then we will parse the number. Now we can just look at a number and do it very quickly. Or we can write these computations like this. So 4825 can be written as 4000 plus 800 plus 20 plus 5. And breaking it down even further, we can write the numbers in this way, where we can start to see the base 10 operation, the power of 10. So we say 4 into 10 raised to the power, 4 into 1110, that can again be rewritten as 4 is to 10 is to the power 3, 2, 1, and 0. And some of you who are software engineers would quickly understand like this is exactly the way we use to convert base 10 to base 2 or base 10 to base 8, where we take the position of the number and we multiply it with the base raised to the power, the position from the right side. So each position in a multi-digit number has a particular meaning as shown in the following diagram. The 7 boxes shown here let us represent any number from 0 through 9,999,999. So each position, and yeah, this is I think the American system where they all have consistent gaps of 3 commas. In India, we have a 3-2-2 system. Each position corresponds to the power of 10. We don't need a special symbol for 10 because we set 1 in a different position and we use 0 as a placeholder. What's also really nice is the fractional quantities shown as digit to the right of a decimal point follows the same pattern. The number 42705.684 can also be written as 4 into 10,000, 2 into 1000, 7 into 100, 0 into 10, plus 5 into 1, so 0 into 10 is still 0. 6 divided by 10, yeah, once you cross the decimal, it becomes like a division, and then it just starts increasing again. So 6 by 10, 8 by 10, and 4 by 10. So this becomes 0 0.6, 0 0.08, and 0 0.004. And if you add all of them, it becomes 0 0.684. This number can also be written without any division like this. So you can, instead of, it's very simple, instead of doing 10, 100,000, you can also multiply it with 0 0.1, 0 0.01, and 0 0.001. So based on how your mind works, like one of these paths, you will find it easy to parse. And then if you convert that into power of 10, it becomes like 10 to the power 4, 3, 2, 1, 0, minus 1, minus 2, minus 3. So you can see there is a reason why we write the things the way we do. So you can notice how the exponents go down to 0 and then become negative numbers. We know that 3 plus 4 equals 7. Similarly, 30 plus 40 equals 70. Similarly, 300 plus 400 equals 700 and 3000 plus 4000 equals 7000. This is the beauty of Hindu Arabic system. When you add decimal numbers of any length, you follow a procedure that breaks down the problem into steps. Each step involves nothing more complicated than adding a pair of single digit numbers. And that's why someone a long time ago forced you to memorize an addition table. And this, I think, we learned it in a different way. So instead of we learning an additional table, we learned it more as a mathematical table. And I think that's what it is going to talk in the next one. So this is basically is very simple. You pick like a row and you pick like a column, and then you can see like 4 plus 1 is 5, 4 plus 4 is 8, and so on. Find the two numbers you wish to add in the top row in the left column. Follow down to get across the sum. For example, 4 plus 6 equal 10. So if I can see either 4 plus 6 or I can see 6 plus 4. Similarly, when you need to multiply two decimal numbers, you must follow a somewhat more complicated procedure, but the one still that breaks down the problem so that you need to do nothing more complex than adding or multiplying single digit decimal numbers. Your early schooling probably also entailed memorizing a multiplication table, and this we all remember, right? Like 2 to 10, and then we started, I think, memorizing even more. And all you need to do to multiply or divide anything is just this. And you can break down any largest amount of calculation into simple by following some rules, which is also how an algorithm works. What's best about the positional system of notation isn't how well it works, but how well it works for counting systems not based on 10. Our number system is not necessarily appropriate for everyone. One big problem with our base 10 system of numbers is that it does not have any relevance for cartoon characters. Most cartoon characters have only 4 fingers on each hand or a paw, so they prefer a number system that is based on 8. Interestingly enough, much of what we know about decimal numbering can be applied to numbering systems more appropriate for our friends in cartoon. And this was chapter 7, and I think we are probably now going to talk about alternatives to 10 later on. And we will talk about like how hexadecimal, octal, binary, these things came to be and why we use the certain number systems the way we use. So I'll stop sharing. This was today's session. Any questions?